Hello everyone, welcome to the tutorial number 19 of IIT-JAM in chemistry, and we are going to discuss law of equipartition of energy and molecular basis of heat capacities in the lecture number 5 of the physical chemistry chapter, gaseous state. But before starting the equipartition principle, we have to have some idea about the degree of freedom. So what about the degree of freedom of a molecule? The degrees of freedom of a particle is defined as the number of coordinates necessary to describe the positions of a particle. So here, a particle has three axes, the x-axis, y-axis and z-axis. Now, in case of a molecule, it may be monatomic, diatomic or polyatomic. So in that case, each and every atom has three axes, the x-axis, y-axis and z-axis. Now here are two molecules. One is a diatomic molecule and this is by default a linear molecule, and this is a triatomic molecule. This is non-linear. Now the number of atoms in this molecule, here it is 3, here it is 2. So this is in general taken to be n. In that case, if it is n, then each atom has three axes. That means 3 degrees of freedom. So if it is 2, then it is 6. If it is 3, then it is 9. So if it is n, then it is 3n number of degrees of freedom. Therefore, the coordinates, now out of this 3n, the coordinates required to describe the translational motion. The molecules are associated with 3 types of motions: translational, rotational and vibrational. Now, to describe the translational motion, only 3 coordinates are required. So out of these 3 are utilized in describing the translational motion. So how many are left? 3n minus 3 are left in order to describe the internal motions. So what about the internal motions? The internal motions are the rotational motions and the vibrational motions. Now rotational motions have 3 degrees of freedom according to the 3 axes. Suppose x-axis is the axis of rotation, then along yz plane the rotation would take place. If y is the axis of rotation, then along xz plane the rotation would take place. Or if z is the axis of rotation, then along the xy plane the rotation would take place. So 3 degrees of freedom are there for rotational motion. But if the molecule is linear in nature, then 1 would be cancelled. In that case, 2 will be the degree of freedom for rotation. Why? Because suppose this is the linear molecule and this is here aligning along the y-axis. So if y-axis is the axis of rotation, then nothing would be visible along the xz plane. That's why this degree of freedom is cancelled here. Therefore, for linear molecule, the degree of freedom is 2, whereas for non-linear molecule it is 3. So what about the number of vibrational motions or vibrational degree of freedom for a linear molecule? For a linear molecule, we have to deduct 2 from 3n minus 3, and it is finally 3n minus 5. And for a non-linear molecule, as it is said that the number of rotational degrees of freedom is 3, therefore 3 has to be deducted from 3n minus 3, and the final result is 3n minus 6. The translational and rotational motions are associated with kinetic energy only, but vibrational motion has both kinetic energy as well as potential energy. Therefore, vibrational energy should be multiplied by 2. But before that, let's have the expression of the different energies. Here, the translational kinetic energy. It is energy of translation, ET, and definitely it is half mv squared. Okay, and if this v is along x-axis, then it is half mvx squared. This is equation number 25. This is about translational kinetic energy, and here m is mass of the molecule and vx is velocity component along x-axis. Now for rotational kinetic energy, it is expressed as half I omega x squared. So I is the moment of inertia along x-axis and omega x is the angular velocity along x-axis. Then in that case the energy of rotation is half I omega squared, and for x-axis it is omega x squared. And this is equation number 26. Now for vibration there are two types of energies. One is vibrational kinetic energy. So energy vibrational kinetic EVK, it is half mu v squared. Mu is the reduced mass. We know that for any molecule, if m1, m2, m3 etc are the masses of different atoms, then its reduced mass, if its reduced mass is mu, then 1 over mu is the reciprocal of m1 plus the reciprocal of m2. That means 1 by m1 plus 1 by m2 plus 1 by m3 plus dot dot dot. For a diatomic molecule, it is 1 by mu equals to 1 by m1 plus 1 by m2. So this is reduced mass. And Vx particularly is vibrational velocity of the atoms along x-axis. Okay, here x should be suffixed. Yeah, here I have made the correction. It is half mu Vx squared. So mu is the reduced mass and Vx is the vibrational velocity of the atoms along x-axis. And finally, vibrational potential energy has the expression energy vibrational potential half k prime x squared. And in this equation number 28, what about x prime, k prime? K prime is the force constant. Okay, this is kind of proportionality constant, and x is the displacement of the atoms from the equilibrium internuclear distance. So this is the force constant and this is the displacement, and in that case the vibrational potential energy is calculated according to the equation number 28. Okay, now law of equipartition of energy. What is this law? This law states that the total energy possessed by a molecule is equally distributed among its different degrees of freedom. The energy distribution for each component is equal to half kT. Okay, this is obtained from actually the relationship 3 by 2 kT equals to half mc square. Okay, and just take into consideration, you will find that E equals to 3 by 2 kT, and 3 by 2 kT has 3 components, therefore each component is half kT. So from that it has been obtained, and this is the law of equipartition of energy, or the theory of equipartition of energy, or the principle of equipartition of energy. So I once again read this out. The total energy possessed by a molecule is equally distributed among its different degrees of freedom. That means if degrees of freedom is suppose 3, then it is 3 into half kT. If it is 10, then it is 10 into half kT. Okay, this way each component is half kT. Okay, so we have just to calculate the degree of freedom, then multiply with half kT. Then the heat capacity would be obtained. Therefore, one more thing, if it is for a 1 mole substance, this is Boltzmann constant for 1 molecule, and for if it is multiplied by Na, Avogadro number, then it becomes R. So it becomes half RT for 1 mole substance. Now energy distribution in linear molecule. Okay, for a linear molecule, translational motion has 3 energy components. Therefore, the overall kinetic energy contribution, it is 3 into half kT from translational motions. And for rotational motions, it has 2 energy components. Therefore, 2 into half kT. Now, what about vibration? Vibration should be 3n minus 5, but it has been multiplied by 2 because it has 2 components. One is kinetic, another is potential. Therefore, it is multiplied by 2. And what about the energy? Degree of freedom into half kT. So 2 into 3n minus 5 is the degree of freedom, vibrational degree of freedom, and half kT is the each energy of each component. Therefore, what about the total energy? Here we have mentioned this, why this 2 has been multiplied here. For vibrational motion, the factor is multiplied by 2 because it is associated with both kinetic and potential energies, whereas rotational motion is kinetic in nature and translational motion is also obviously kinetic in nature. The potential energies in these two cases do not apply. Now, total molecular energy. For each molecule, it is denoted as epsilon. So it is 3 into half kT plus 2 into half kT plus 2 into 3n minus 5 into half kT. So here all these are written. This is equation number 29. And if it is multiplied by Na, then it becomes the molar energy. That means E, capital E. This capital E is this one, the same expression, but in place of K, we are using here R. That means Na has been multiplied in the both sides of the equation number 29. So on multiplying epsilon with Na, it becomes total energy E, and on multiplying Na in the right hand side, all the K terms are converted into R terms. So it is 3 into half RT, 2 plus 2 into half RT plus 2 into 3n minus 5 into half RT, and this is equation number 30 and applicable for any kind of linear molecule. Now, this same distribution for a non-linear molecule. Translational motion is has three components, so the energy is 3 into half kT. But for rotation, instead of 2, as we have calculated in the previous one for a linear molecule, it is 3 for a non-linear molecule, and definitely it is 3 into half kT instead of 2 into half kT like was the previous one. And vibrational motion, we have calculated in place of 3n minus 5, we are writing here 3n minus 6, and it is multiplied by 2 as usual for vibrational motion having both kinetic and potential energies. Therefore, the energy is due to vibration is 2 into 3n minus 6 into half kT. Therefore, the total molecular energy is the sum of these three. And for molar energy, in place of K we are using R, and in place of epsilon we are using capital E. Thus we get equation number 31 and 32. 31 represents the molecular kinetic total energy, and equation number 32 describes the molar total energy. Now, heat capacity, and how does it develop from the molecules? In generally, we know that the definition of heat capacity is what? It is the energy required to increase the temperature of a substance, 1 mole of a substance by 1 degree is known as heat capacity. So if Q is the overall amount of heat absorbed for increasing the temperature of 1 mole of substance by 1 degree, then dQ by dt equals to heat capacity C. But for gaseous substances, there are two types of heat capacities. One is the heat capacity at constant volume, and another is the heat capacity at constant pressure. So, heat capacity at constant volume is CV. Sometimes it is also written as CV, M. That means for 1 mole substance. But since it is heat capacity and it is a molar property, so this M is not written here in this lecture. Now, the expression of CV is the exchange of heat at constant volume per unit temperature, that is dQ by dt at constant V, and this is nothing but the rate of change in internal energy with respect to temperature at constant volume, that is du by dt at constant V. So thus we get equation number 33, and Cp is the energy change at constant pressure. This is equation number 34. So the expression is Cp equals to dQ by dt at constant pressure. And from the first law of thermodynamics, we know its mathematical form. It is dQ equal to du plus P dV. And by differentiating both sides with respect to temperature at constant pressure, in the left hand side dQ is converted into dq dt P, du is converted into du dt P, and pdv is converted into P into dv dt P. Thus we get equation number 35. Now from equation here we get Cp, the expression of Cp in equation 34. Therefore in place of dq dt P, here dq dt P, we just put Cp here from equation 34 to equation 35. Then this equation number 35 becomes Cp equals to this one, this parameters in the right hand sides. So in equation number 35 we put dq by dt P equals to Cp, which has been derived from equation number 34. Thus we get the relationship Cp equals to du by dt at constant pressure into P plus dv by dt at constant pressure, and this way we get equation number 36. Now for 1 mole of an ideal gas, Pv equal to RT, we know that, and if it is differentiated, and both sides are differentiated with respect to temperature at constant pressure, then it gives the result P into dv dt P equals to R, and this equation 36 now can be temporarily written as Cp equals to du dt P plus in place of this R. So this is equation number 36.a. This is the temporary form of equation number 36. And finally, from the Joule's experiment, we know that du dt P equals to du dt V also for an ideal gas. Therefore, we put here du dt P. In place of du dt P, we can put here du dt V. But from equation number 34, the du dt V is actually equal to the heat capacity at constant volume, Cv. So here in this equation number 36a, we can easily write Cv, and this way we get equation number 37, which is actually Cp equals to Cv plus R, and we all know about this, that Cp minus Cv equals to R. Here in this equation number 37, this fact is being reflected. So now our objective is to find out the value of Cv. Cv is actually the arising out from the internal energy of the molecule. That is it is arising out from different degrees of freedom. So we can calculate this Cv from the different degrees of freedom, and also by adding R we can get the value of Cp also. So energy E of a gas, it can be obtained from the equipartition principle, and this is nothing but equal to the internal energy of the gas. So in that case we can easily write that du dt V, this expression is nothing but dE dt V, where U is the internal energy and E is the total molecular energy which is obtained from the equipartition principle. Hence this is actually the heat capacity at constant volume. So according to this equation number 38, we can easily calculate heat capacity at constant volume just by taking the differentiation of the energy expressions with respect to temperature at constant volume. So let's start calculating the different heat capacities, and simultaneously the Poisson's ratio. Poisson's ratio is Cp by Cp. So let's start from the monatomic gas, for example helium, neon, argon, etc. So in a monatomic ideal gas, is there any rotation? No, you cannot observe any kind of rotation. If still there is a rotation, it is invisible for being monatomic, and since there is no chemical bonding, so vibration would also be absent there. Only translational motion, and its degree of freedom is 3. Therefore the energy contribution due to its translation is 3 into half RT, that is 3 by 2 RT for 1 molar gas. Therefore the expression of Cv is dE by dt. That means we have to differentiate this with respect to temperature at constant volume, and if we do so, then we shall get the value 3 by 2 R. So Cv equals to 3 by 2 R. Therefore Cp 3 by 2 R plus R equals to 5 by 2 R. Now the Poisson's ratio gamma, it is Cp by Cv, and the ratio is finally 5 by 3 equals to 1.67. So this is about monatomic gas. Now for a diatomic gas, by default any diatomic gas is linear in nature. Therefore for a diatomic gas the energy expression should be obtained or borrowed from equation number 30. It is 3 into half RT plus 2 into half RT plus 2 into 3 minus 5 into half RT. Now, for a diatomic molecule, the value of N is equal to 2. So let's put 2 in place of N, and this way we get this next expression, and by adding we get the value 7 by 2 RT. So this is the value of energy. Now we have to differentiate this with respect to temperature, and if we do so, then this T will just vanish and only 7 by 2 R would be left. Therefore, the CV, that is the heat capacity of any diatomic gas, is theoretically 7 by 2 R or 3.5 R. Therefore, Cp equals to the expression of Cv plus R. That means 7 by 2 R plus R, that is here it is 9 by 2 R. Therefore, the Poisson ratio gamma equals to Cp by Cv equals to 9 by 7 equals to 1.286. Now let's calculate this for a linear triatomic molecule, for example HCN, carbon dioxide, etc. For all these molecules, the value of N is equal to 3. That is, there are 3 number of atoms, and in that case again we can apply equation number 30, and this way this is the expression. Now we have to put 3 in place of this N. Then we can easily calculate 3 into 3, 3 times 3 equals to 9, 9 minus 5 equals to 4, 4 into 2 equal to 8, 8 plus 2 equals to 10, 10 plus 3 equals to 13, that is 13 into half RT, 13 by 2 RT. Okay, so this is the energy. Now we have to differentiate this with respect to temperature at constant volume, and the result is 13 by 2 R. T has disappeared. So if this is the expression of Cv, then what is the expression of Cp? Just add another R with Cv, and thus you will get the value 15 by 2. Therefore Cp equals to 15 by 2 R. And what about its Poisson ratio? By the similar type of calculation, we can get the Poisson ratio for this molecule also, and this is 1.15. And for a non-linear molecule, for example hydrogen sulfide, nitrogen dioxide, or ozone, the calculation goes on like this. For a non-linear triatomic gas, N equals to 3, number of atoms equal to 3. Therefore equation number 32 can be written here in terms of energy equals to function of temperature. So equation number 32 here, and just put the value 3 in place of N. Then it is 3 into 3 times 3 means 9, 9 minus 6 means 3, then 3 times 2 equals to 6, so it is 6, 7, 8, 9, 10, 11, 12, so 12 into half RT, that is it is 6 RT. Therefore Cv equals to 6R, because the differentiation would make this T expression vanished here. So Cv, if Cv equals to 6R, then Cp must be 7R, because of this rule as we have obtained. Just add any R. Therefore the Poisson ratio should be 7 by 6, and it is 1.167. So that's all about this theory of equipartition of energy. Now let's discuss some questions here. The first question, as a continuation from the previous lectures, it is question number 15 of this gaseous chapter, and the question is, for an N atom non-linear polyatomic gas, the constant volume molar heat capacity, look here, as just I have said that some comma m is added, but we shall not write this, simply it is Cv. So it has the expected value of 3 into n minus 1 R, and you have to say, we know that this is based on the principle of equipartition energy. And what about the correct statements? That means there may be any one statement or more than one statement also. This is MSQ type of question, multiple short question. So the measured Cv is independent of temperature. Never, it cannot be independent of temperature. We have to always put the temperature as its function. Now the measured is dependent on temperature. So It is not independent, it is actually dependent of temperature. So this statement is correct, definitely. And C, the measured CBM is typically lower than the expected value. Yes, this is another fact, that when you are measuring the value of CB by experimental method, then you will find that it is much lower than the calculated value. So this C statement is also correct. Now what about the final statement? It states that the measured CV is typically higher than the expected value. No, this is wrong, because C option is correct option. Therefore options B and C are the correct options. Yeah, therefore option B and C are the correct statements. Now the next question, it says that it came in IIT-JAM 2022. And what about the previous question? It came in IIT-JAM 2022, and this one also came in 2022. What is the question? At constant volume, 1.0 kilojoule, that means 1000 joule of heat is transferred to 2 moles of an ideal gas at 1 atmospheric pressure and 298 Kelvin. The final temperature you have to calculate in the Kelvin unit after rounding it off, and the value of R is given here to be 8.314 joule per Kelvin per mole. So let's calculate the answer here. So we know that CV equals to 3 by 2 R for degree of freedom 3. For any type of ideal gas, it is supposed to be a monatomic gas, and in that case the degree of freedom is 3, and therefore the energy is 3 by 2 RT. Therefore the CV value is 3 by 2 R. So for 1 mole substance it is 3 by 2 R. For n mole substance it is NCV, that is n into 3 by 2 R. Therefore here for this number of mole we have taken here 2 moles of the gas, so we are putting 2 here, so it is 2 into 3 by 2 R, that is 3 R, and this is actually the value of delta Q over delta T, that is the heat supplied over the temperature increase. Therefore we have the values of delta Q and R is given already, and the relation is delta Q by delta T equals to 3R. That means delta T equals to delta Q by 3R. So the value of delta Q equals to 1000 and the value of R equals to 8.314, and the result is 40 Kelvin. So there is an increase in 40 Kelvin from 298. So 298 plus 40 equals to 338 Kelvin. So here in the blank space you have to just enter type 3 data, 3, 3 and 8, then given enter. So 338 is the answer. And now next on to the next question, number 17, and it came in 2011, and the question is, based on the principle of equipartition of energy, the molar heat capacity of carbon dioxide at constant volume CV is which one out of these four options? And here also it is comma M, but we are not writing this comma M term, we are just writing it as CV. So let's find out the answer. CV is a linear triatomic molecule, therefore equation number 32 is taken into consideration here. Equation number 30, I'm sorry, it's not 32, it's equation number 30, and according to equation number 30 it is equals to 3 into half RT. This is for translational, 2 into half RT, this is for rotational, and 2 into 3 minus 5 into half RT, this is vibrational. Now the value for being a triatomic molecule, the value of N is 3, so it is 3 into 3 minus 5, so it is 9 minus 5, 9 minus 5 means 4, 4 into 2, that is 8, 9, 10, 11, 12, 13, that is 13 by 2 RT, that is 6.5 RT. So let's differentiate this with respect to temperature in order to get the value of CV. Therefore the value of CV is 6.5 R as usual. Therefore this option is the correct answer, option C. Next question, question number 18. According to this is the last question of this lecture. So according to the equipartition principle of energy, the molar heat capacity at constant volume for carbon dioxide, sulfur dioxide and H2O water, it follows the trend out of these four, which one is correct, and this came in 2014. Here Carbon dioxide is a linear triatomic molecule, while sulfur dioxide is linear, but it is non-linear, but it's triatomic, and water is also triatomic but non-linear. Okay, so for these two, for linear molecule it's 6.5 R. We have already calculated this, and for non-linear molecule it is 6 R. Therefore, these two have the same value, but carbon dioxide should have some greater value, and it is 6.5 R. Therefore, this option B is the correct answer. So that's all for today. No, there is one more question. Okay, fine. And the question is, according to the equipartition principle, the predicted high temperature limiting value of the molar heat capacity at constant volume for acetylene is which one is correct? So this is a tetraatomic molecule, and the value of n equals to 4 here. Therefore, for a linear molecule, the same equation according to equation number 30, and we have to put just 4 here in place of n, and the value is finally 9.5 RT. So Cv is 9.5 R. Therefore, option D is the correct answer. One more question here, question number 20. The value of Cv for 1 mole of nitrogen gas predicted for principle of equipartition energy, ignoring vibrational contributions. So we cannot take into consideration the vibrational energy, and we have to find the value in joule per Kelvin per mole unit after rounding it up to 2 decimal places. It came in 2020, and the answer, if the vibrational contribution is ignored, then nitrogen has 3 translational and 2 rotational degrees of freedom, because by default nitrogen is a linear molecule, therefore it should have 2 rotational degrees of freedom, and therefore it has total 5 degrees of freedom, and hence its energy is 2.5 RT. Therefore Cv is definitely 2.5 R, and the value is 20.785, and after rounding it off up to 2 decimal place, it is 20.79 joule per Kelvin per mole. So right now we can say thank you for showing patience in listening to this lecture. So have a nice day.